Let me show you, or at least indicate, how exactly the least squares estimates, least squares estimates in regression is actually coming up as they are. The least squares criterion is the sum of the y observations minus the line squared. This is the term, this is the least square term that we would like to minimize. So the xi's are known, the yi's are known, and we will see it mathematically as a function of the unknown intercept and slope, and we want to find the a and the b intercept and slope that minimizes this one. That is the least squares criterion. How do we minimize functions of two variables in mathematics? We go look for the derivative of each of those. So first the derivative with respect to a, and then is setting that equal to 0, and then we try to solve, and then we see what comes out of it. Now, if I look at this function up here, the derivative, first of all, we have the outer function. So the outer function, when we take the derivative, that is the square, this whole thing squared. So the derivative is 2 times this whole thing squared, actually. That is the outer function. What about the inner function? No, that is how we do the derivative of a composite function. What is the inner function? That's what we have inside here. Sorry, I shouldn't, of course. Let me just. I shouldn't have the square here, of course. When I do the derivative of x squared, I get 2x. So that was a little mistake there. Like this. Then I should still have the derivative of the inner function with respect to a. Well, this is a constant, this is a constant when it comes to a, and only a -1 appears as a consequence of taking the derivative with respect to a there. Then we equalize this to 0, and we would at least, let's do a first solution step here by taking in the sums here. I remove the 2 and the -1, or rather multiply it away. So I would have the sum of yi. I would have minus n times a minus b times the sum of xi equaling 0. That is at least the first step. Let's move on before we do anything more and look at the derivative with respect to b here. Again, the outer function derivative becomes exactly the same. yi minus a minus b xi. And then when I take the inner function derivative with respect to b, only the minus xi occurs. So it's times minus xi. I equalize this to 0 for solving. Then let's do a first step of the solving to see that the 2 disappears, and I could express it as the sum of xi yi equaling the same as na minus, and then I take a plus because I move it to the other side of the equal sign, minus, actually, sorry, it should be minus because I have a minus there and I have a minus there. This is plus. I move to the other side of the sign, and I would have b times the sum of squared x, because this x multiplies with this x. So this would be at least the 2 main equations that I should solve for a and b. I should solve this for a and b. Let's see if we take this, the first one here. we could express it in terms if we divide through by n, this one, we have actually that says y bar equaling a plus bx bar. Actually, that comes directly out of this, that if we know b, we can compute a. That's at least one way of expressing it, just by using the means of x and means of y. Now, as I'm just solving two equations with two unknowns here in a sort of standard or basic, maybe a bit naive way, but still, let me plug in. We could also say that a equals y bar minus b x bar. I can plug in this a in the other equation and express it as follows. I'd use the other one here, xy. And then if I say n times a, let me just make sure that do I actually have, I did a mistake here, that's why I'm getting confused. I did a mistake up here because I forgot that I needed to go with the xi minus xi with the minus a. So in fact, and then in fact also there is the minus on the y, so altogether this is not na, it would actually be, sorry about this term would be instead a times the sum of xi. It's getting a bit not so nice, and it'll be the sum, because so the sum of xi yi is the same as a sum of xi b times sum of xi squared, actually. Sorry about this. So if I plug in a here in this correct version of this second equation, if I plug in a, I have y bar minus b bar x bar times the sum of xi plus b times the sum of xi squared. Now I can solve for b, and I will not go through each, we need one or two steps, but the fact is, if you solve this for b, you will see that it becomes the sum of xi yi minus y bar times the sum of xi. It becomes divided by the sum of xi squared minus x bar times the sum of xi, which in fact is, using the knowledge of hand calculation formulas, sxy divided by sxx. And then we have at least found the solutions to this solving, to putting the derivatives equal to 0. By this one and by this one, we have the formulas for a and b. What we should still prove, but I'm going to jump this, we should prove it to be a minimum, actually. And there is also mathematical ways of doing that. I will skip that. We could take the second derivative of ab with respect to a squared, and the second derivative of ab with respect to b squared, and so on. And then we could take the matrix and show that it's positive definite by looking at the eigenvalues. I will skip those mathematical details. It's not extremely difficult if you know how to prove, how to do this from optimization of two-dimensional functions. So find these second derivatives, put them into a 2x2 matrix, find the eigenvalues, show that both of the eigenvalues are positive, which can be shown here, which means that this is a minimum. So this is the proof, as far as I will take it, of how to achieve the least squares estimates as we have seen them now. Thank you.